I'm Andrew Wang, and this is my Physics 2212 Lab 4 report. So to introduce, the purpose of the lab was to predict the behavior of circuits with resistors in series and in parallel, to measure the current and potential difference, and to examine the behavior of capacitors and resistance. Important concepts and formulas used was the node rule, the loop rule, Ohm's law, and the given formula for calculating RC. The experimental conditions. The system was the circuit, and the surroundings was everything else in the universe. Assumptions made was to ignore resistance and the wire and in the ammeter. And in the setup, I used the online circuit builder with PHYS to simulate the circuits. For part A, the prediction was that the circuit was going to be 0.02 amps all around. And the results was indeed that for both parts. Before and after the battery, the current did not change. If you reverse the current, it was negative 0.02 amps, so it was flipped, but the magnitude remained the same. When one ammeter was replaced with a voltmeter, the voltmeter had a potential difference of 3, and the ammeter was 0. This is because the resistance of the voltmeter is too high to allow the current to go through. But the current before the voltmeter is still 0.2 amps. The sum of the potential difference at every point, from A to B, from C to D, E to F, G to H, etc. You add them all together, and it's going to be the potential difference is going to be 0. The below graph visualizes it. It goes up, but in the end, it still comes down to 0, because that's how series circuits work. If you added an ammeter in parallel with a resistor, the current increases to 0.06 amps because the currents will avoid the path with the higher resistance, meaning the current will be a bit higher. The resistance measured was that for the 47 ohm resistor, it was 47 ohms. Same thing with the 100 ohm resistor. The wire had no resistance, and the ammeter had no resistance. Now, obviously, this is for an ideal scenario only. For part B, for the RC circuit, in the very, very beginning, the lights are bright when powered at the start, but as the capacitor gets charged, the bulb dims over time until it is completely off. When the battery is disconnected, the capacitor discharges again, and the bulb starts bright again before slowly dimming again. The time to discharge for the 10 ohm bulb was 9 seconds, and the time to discharge for the 20 ohm light bulb was 17 seconds. Now, if you use the formula and you graphed it over time, the slope would be negative 0.167. The RC is one over the slope, so if you apply that, then you get RC as 5.988 seconds. The calculated RC would be 30 times 0.2. That's 6 seconds. So it's very close, but it's a tiny bit off. Potential sources of error. There wasn't many sources of error because because almost everything was done through the computer model. The only thing that was a human that could be a victim to human error was the time measurements. I had to use the stopwatch, so there may have been errors caused by me there. Conclusion. What if you're doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? While the virtual ammeter has 0 resistance because it is ideal, a real ammeter would have some resistance. This would mean a different potential difference and different current readings. So that would change the numbers up for everything. What if you were doing this lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? If a capacitor has no resistor, capacitors would charge instantly in an ideal environment. In real life, this is not possible because the wires also have some resistance. Thank you. That is my lab 4 presentation. Thank you very much for watching.